Students, welcome to Sunil's tutorial. I'm Sunil Midwani and today we'll be doing this chapter called as magnetism. Let's see this. How do I classify magnetic substances? Classify magnetic substances. How do I classify magnetic substances? Now, according to their magnetic properties, substances are classified into three different types. According to their properties, magnetic properties, substances are classified into first diamagnetic substances, second paramagnetic substances, and third ferromagnetic substances. These are the three different types of substances that you can have. Question: why should a substance behave like a magnet? Before we see what are the different types of substances, magnetic substances, let us understand the reason why a substance would behave like a magnet. Magnetic property of a substance. Let's try to see the magnetic property of a substance. Now, an atom is made up of a central nucleus called central core called as nucleus, which carries a positive charge surrounded by negatively charged electrons which are revolving in different orbits around it. Right? An atom has a central massive core called nucleus, which carries positive charge and is surrounded by negatively charged electrons revolving in different orbits. Right? Now, these orbiting electrons around the nucleus constitute electric current because electrons are negatively charged particles. When a charged particle moves, that gives rise to current. So I can say that these orbiting electrons constitute current. Right? Now if there is current, that means these electrons are moving in circular orbit, that means they are making current loop. Now, when current flows through a conductor, that gives rise to a magnetic field. So I can say that there are equivalent current loops and hence they possess magnetic dipole moment. They are equivalent current loops. These are equivalent current loops and hence possess magnetic dipole. So these substances give rise to the magnetic property. Now, see, you have electron revolving around the nucleus. Electron is a charged particle. As a charged particle moves, it gives rise to current. When current flows through a conductor, that gives rise to a magnetic field. That's exactly what I've written. Right? Is this clear? Now, that means we are very sure that magnetic field is produced because of current moving in circular orbits around the nucleus. Now we have a problem. Some of these electrons circulate clockwise whereas some rotate anti-clockwise. Some electrons rotate clockwise whereas some rotate anti-clockwise. Some of these electrons rotate clockwise whereas some rotate anti-clockwise. Moreover, these electrons also have these electrons also spin on their own axis. Moreover, electrons also spin about their own axis. Electrons also spin about their own axis, right? Now, because of this spinning about their own axis also, they are going to possess some motion. Charged particle moving means that gives rise to current, current gives rise to a magnetic field, right? And they possess some dipole moment. They possess some dipole moment due to the spin motion. So they have you have magnetic loop that is produced due to the movement of the current. Now due to the current that is produced. Now as the electron rotates clockwise, it produces a particular current. It produces a particular magnetic field. As it rotates anti-clockwise, it produces a different magnetic field. As the electron spins in clockwise direction, it produces a magnetic field. As it spins anti-clockwise, it produces some other magnetic field, right? That means the net magnetic dipole that is going to be produced is going to be the vector sum of all these magnetic fields, right? The net magnetic dipole moment of each electron, the net magnetic moment of each electron is equal to the vector sum of the dipole moment is equal to the vector sum of the dipole moment due to the orbital motion and the spin motion. So you have magnetic moment of each electron is going to be nothing but the vector sum of all this. That's how a magnetic field is produced inside the substance. Now, we had said that magnetic substances are classified into three: paramagnetic, diamagnetic and ferromagnetic. What is the difference between them? Right? Let's first see what is diamagnetic substances. What are diamagnetic substances? Now, in case of some substances, the dipole moment of electrons in each atom cancels each other and the net magnetic dipole moment is zero. We said that the net magnetic dipole moment of a substance the net magnetic dipole of a substance is going to be nothing but the vector sum of all the magnetic dipole. Now if this vector sum comes out to be 0, then that substance is called as a diamagnetic substance. Fine, do we get this thing here? So I can say that in case of atoms of some substances, in case of atoms of some substances, the dipole moment of the electrons, in each atom cancel each other, and the magnetic dipole moment in each atom is 0, and the magnetic dipole moment in each atom is 0. Right? Such substances are called as diamagnetic substances. So such substances are called diamagnetic substances. Right, so do you understand what are diamagnetic substances? These are those substances in which the vector sum of the magnetic dipole moment due to the spin motion and due to the rotational motion of the electron is 0. Fine. Now let us see how do they behave if they are diamagnetic substances. When they are placed in an external magnetic field, there is a change in the magnetic flux associated with the electron. There is already magnetic flux due to electrons. Now when they are placed in an external magnetic field, the magnetic flux is going to change because of the external magnetic field, right? Now, and that will induce, wait, first let's write this down. When they are placed in external magnetic field, when they are placed in external magnetic field, there is a change in the magnetic flux associated with each electron. There is a change in magnetic flux associated with each electron. Now a change in magnetic flux, we know, results in an EMF. A change in magnetic flux produces EMF. So I can say which produces an EMF in them. Which produces an EMF, electromotive force. Now, due to this EMF, some electrons circulating in one direction are accelerated and some circulating in opposite direction are retarded. Right? Due to this EMF, there is going to be an EMF that is going to be produced in the substance. I can say due to this EMF, some electrons circulating in one direction are accelerated and some electrons circulating in opposite direction are retarded. Some electrons circulating in opposite direction are retarded. Right? Now, as a result, each atom acquires some net. See, for the timing there was a net magnetic dipole moment which was 0. Now, due to this EMF, there is going to be some net magnetic dipole moment because some electrons in one direction are moving with higher acceleration. That means they will produce a greater magnetic field. So there will be some net magnetic field in one direction that will give to a magnetic dipole moment, right? So I can say that as a result, each atom acquires some net magnetic dipole moment and the diamagnetic substance gets magnetized. As a result, each atom acquires net magnetic dipole moment and the diamagnetic substance gets magnetized. And diamagnetic substance gets magnetized. Fine, do you get this thing clear? That's the reason why diamagnetic substance gets magnetized. Now, the resultant magnetic dipole that is going to be produced is in opposite direction to the applied magnetic field. The resultant, in this case, the resultant magnetic dipole moment is opposite in opposite direction to the applied magnetic field. Fine. So as a result, the diamagnetic substance is repelled from the magnet, since obviously if it is going to produce an opposite magnetic field to that of the external magnetic field, it is going to get repelled from the substance. So as a result, the diamagnetic substance is repelled. Diamagnetic substance is repelled by the magnet. The diamagnetic substance is repelled by the magnet. Also, if it is suspended in a magnetic field, it will set itself at right angle to the direction of the field. If it is suspended in a magnetic field, it is suspended in a magnetic field, it sets itself at right angles to the direction of the field. At right angles to the direction of the field. So these are diamagnetic substances. Fine, do we get this thing here? Now let's try to understand the molecular model of paramagnetic substances. Next, paramagnetic substances. Now, what are paramagnetic substances? Now, in some substances, it so happens that the magnetic dipole associated with each atom does not cancel out. As a result, each atom of the substance has a resultant dipole moment, and such substances are called as paramagnetic substances. Question. So, what is the difference in diamagnetic and paramagnetic substances? In diamagnetic substances, it would cancel each other. The magnetic dipole moment would cancel each other. In paramagnetic substances, it does not cancel each other. Right? So there is some small resultant magnetic dipole moment. Right? Now, it so happens that because of heat and other external factors, due to the motion of the electron, there is some small magnetic property that is present on it. There is some small magnetic dipole that is present on the substance. But due to heat and random thermal motion of the electron, this magnetic dipole moment that is produced in the substance gets lost. So when you look at it, both the substances ideally at room temperature, both of them do not have any magnetic property. But in the case of diamagnetic substance, there was never a magnetic property that was present because the magnetic dipole moments were so aligned that they would cancel each other. Here, the magnetic dipole moment which was produced due to the motion of the electron was so aligned that there was a magnetic property, but due to random thermal motion, this property got cancelled. Do you get this thing clear? So I can say that in some substances, the magnetic dipole moment associated with each atom does not cancel out. As a result, each atom of such substance possesses as a resultant dipole moment. Such substances are called as paramagnetic substances. Substances are called paramagnetic substances. Such substances are called as paramagnetic substances. Each atom of the paramagnetic substance behaves like a tiny atomic dipole. Each atom of paramagnetic substance behaves like a tiny atomic dipole. Each atom of the paramagnetic substance behaves like a tiny atomic dipole.
So what do you mean by this?
That means there is some magnetic property there on it. Tiny atomic dipole means it behaves like a tiny magnet. Because the magnetic moment that is produced due to the spin of the electron and the rotation of the electrons in clockwise and anti-clockwise direction is not cancelling. So hence there is some net magnetic force that is, or there is some magnetic dipole that still remains on each atom. So each atom is now behaving like a magnet.
So is it unbalanced?
Yes, it is unbalanced. Right? That's the reason why it is going to cancel each other. If all of them were in one direction, then there would have been a strong magnetic field that would have been produced. Right? I can say however, on account of random thermal motion, associated with the atoms, the magnetic dipole moment of all the atoms, of all atoms get oriented in all possible directions. What you were saying, unbalanced. Get oriented in all possible directions. Right? So they get oriented in all possible directions. As a result, what will happen is, as a result, the material has no net magnetic dipole moment. The material, as a result, the material has no net magnetic dipole moment. So although each atom is behaving like a magnet, the net magnetic field that is produced by the substance is zero, because these magnets are oriented in all possible directions and the net magnetic field on the substance therefore is zero. Right? Do you get this thing clear? However, if a magnetic field is applied to such substances, now what happens in the presence of an external magnetic field? So I can say that, however, if magnetic field is applied to such substances, if magnetic field is applied to such substances, the magnetic dipole moment of the atomic magnets all of them will get aligned in one direction. Is applied to such substances, the magnetic dipole moment, since all of them are magnetic, dipole moment, the magnetic dipole moment of atomic magnets get aligned in the direction of the magnetic field. In the direction of magnetic field. Right? As a result of this, the material exhibits magnetic property and the material exhibits magnetic property. That's how a paramagnetic substance exhibits magnetic property. Now what happens when the external magnetic field is removed? When external magnetic field is removed, the atomic magnets again get oriented in all possible directions and the magnetic property is lost. When the external magnetic field is removed, the atomic magnets get oriented in all possible directions. The atomic magnets get oriented in all possible directions randomly, and the material loses magnetism. Fine, do you get this in here? Now, it is found that there is a tendency of alignment of the atomic dipole magnet in the direction of the field increases when the applied field is applied. That means when an external magnetic field is applied, all the small tiny atomic dipole will get aligned in the direction of the external magnetic field. Fine, do you get this in here? Now, I can say that there is a tendency, there is a tendency, there is a tendency of alignment there is a tendency of alignment of atomic dipole axis in the direction of the field of the applied field. Fine, do you get this thing here? Now, thus the alignment of the dipole axis in the direction of the field is more pronounced in stronger field and at low temperature. This property is more if the external field is strong and at low temperature. This tendency is more pronounced in stronger fields and at low temperature. Fine, do you get this in here? So, when the atomic dipole axes are aligned in the direction of the field, the substance would achieve maximum magnetization, and therefore there is a limit beyond which magnetization cannot increase. If all the tiny atomic dipoles are aligned in the direction of the field, then if all of them are aligned in one direction, that will give you a certain amount of magnetization of the substance. Now, since there are no other small tiny atomic dipole, magnetic dipole, there would be no further alignment, so that would be the maximum magnetization that you would achieve, right? So I can say that when all the atomic dipole axes, when all the atomic dipole axes are aligned in the direction of the field, the substance achieves maximum magnetization. The substance achieves maximum magnetization. Right? So that's how that substance achieves maximum magnetization. Right? Do you get this in here? Right? Therefore, there is a limit beyond which magnetization cannot be increased. Therefore, there is a limit beyond which magnetization cannot be increased. So there will be a maximum level to which it can be increased. Right? Do we get this thing here? So thus the magnetic moment achieved by a paramagnetic substance placed in an external magnetic field is in the direction of the field. Therefore, there it was in the direction opposite. In the case of diamagnetic substances, it was in the direction opposite to the field. Therefore, it was repelling. Here it is in the direction of the magnetic field. Right? I can say that. Therefore, the magnetic moment achieved by paramagnetic material placed in an external magnetic field in an external magnetic field, placed in an external magnetic field, is in the direction of the field, is in the direction of field, right? Now, therefore, I can say that the substance, when freely suspended in the external magnetic field, will remain parallel to the field and will also get attracted to the magnet. Then it would repel and would remain perpendicular. In the case of diamagnetic substance, when a diamagnetic substance is placed in an external magnetic field, it would align itself in a direction perpendicular to the external magnetic field and would be repelled from the magnetic field. In the case of paramagnetic substances, it would remain parallel to the field and would be attracted towards the field. Right? Do you get this in clear? So I can say, therefore, the substance when freely suspended, the substance when freely suspended, the substance when freely suspended in external magnetic field remains parallel to the field and is also attracted to the field. So those are paramagnetic substances. Next, let's understand what are ferromagnetic substances. Let's try to understand ferromagnetic substances. Now, in the case of ferromagnetic substances, the alignment of the dipole axis in the atom is in the direction of the external field is very high, and hence even with a small external field, there would be a strong magnetic property that would be produced in the substance. Right? Ferromagnetic substances have magnetic dipole axis in each magnet, which are randomly arranged and they cancel each other. But the only difference between paramagnetic and ferromagnetic substances are that when ferromagnetic substances are placed in an external magnetic field, when ferromagnetic substances are placed in a weak external magnetic field, even then the alignment of the tiny magnetic dipole in the direction of the external field is very high. Hence, with a small external field, the ferromagnetic substance would achieve high magnetism. Fine, do you get this thing clear? Yeah. They have properties similar to that of paramagnetic substances. That means each atom behaves like a tiny magnet. Fine. Now, these atoms are randomly arranged and they are going to cancel each other's magnetic field. Therefore, the net magnetic effect on the substance is zero, which is similar to that in the paramagnetic substance. In diamagnetic substance, so there is no net magnetic field at all, right? Which is very similar to what you have in paramagnetic substances. Now, what is the difference here? The difference between paramagnetic and ferromagnetic substances is that when ferromagnetic substances are placed in an external magnetic field, all the tiny atomic dipoles which are randomly arranged inside the substance would immediately get aligned in one direction. Since all of them would get aligned in one direction, the substance would achieve magnetism or magnetic property in that direction. This is achieved even with a very small and a weak external magnetic field. There you needed a strong magnetic field, right? Do you get this thing clear? Moreover, here, if the external magnetic field is removed, the atoms of the ferromagnetic substance retain their magnetization. They would still, even if the external magnetic field is removed, those tiny atomic dipoles would still remain oriented in the same direction. In the case of paramagnetic substances, as soon as the external magnetic field is removed, the atoms would get randomly oriented. No. Here in this case, in ferromagnetic substances, they would still remain aligned in the same direction, and that is the reason why a ferromagnetic substance retains its magnetic property even when the external magnetic field is removed. Fine, do you get this thing here? Can we write this down? I can say in case of atoms, of ferromagnetic substances, the alignment of dipole axis of the atoms in the direction of external magnetic field is quite high, right? Even if the applied field is weak. So that means here you would have high degree of magnetization that would be achieved. I can say moreover, even if the applied field is removed, the atoms of the ferromagnetic material retain some magnetization. The atoms of ferromagnetic material retain some magnetization. Right? So it is for this reason that ferromagnetic substances are used to prepare permanent magnets. Therefore, ferromagnetic substances are used to prepare permanent magnets. Right? So do you understand ferromagnetic material? Now, when ferromagnetic material is placed inside a magnetization field, the magnetic flux of the ferromagnetic material is much larger than in vacuum, right? I can say that when I already told you that all the tiny atomic dipole magnets would align themselves in the direction of the magnetic field. So I can say that therefore you would have a very high magnetic field that would be produced. Fine, do you get this thing here? Next, let's try to see something else. Now, in the case of paramagnetic substances and ferromagnetic substances, both of them have the susceptibility of these substances is inversely proportional to the temperature, is inversely proportional to the excess temperature above the Curie temperature. In both these cases, the extent to which magnetization would take place is inversely proportional to the excess temperature over Curie temperature. Now, what is Curie temperature? Curie temperature is that temperature at which the substance would lose all its magnetization when it is heated, right? Okay, now let's try to explain ferromagnetic substances on the basis of domain theory. This was on the basis of atomic theory. Ferromagnetic substances on basis of domain theory. Now, ferromagnetic substances possess the properties of paramagnetic substances. Their behavior, as I told you, is similar to that of paramagnetic substances, except that when they are placed in even in a weak external magnetic field, all the tiny atomic magnetic dipoles get aligned in the same direction, right? So let's see the domain theory. According to domain theory, a magnetic substance is made up of small number of regions that are called as domains. See, if this is a substance, you have domains practically in every direction, right? Now, so the ferromagnetic substance is made up of small regions which are called as domains, right? The domains are formed due to quantum mechanical effect called as exchange interaction. You have electrons that would move from one orbital to another orbital, that would lead to the formation, right? Due to the interaction of unpaired electrons in one atom strongly with an unpaired electron with the neighboring atom in such a manner that they would spontaneously align themselves in a common direction over a small region. So this alignment of the two electrons in a common region in a small volume is called as a domain. There are two atoms which are close to each other. These electrons of the two atoms would interact with each other. There would be a force of repulsion between common charges. Hence, the two electrons would then align themselves in a particular direction, so that there is minimum force of repulsion between them. They would align themselves in a particular direction over a small region in a very small volume. That region is called as domain. So that's how domains are formed, right? Thus the region or the space over which the magnetic dipole moments are aligned is called as domain. Now this domains, the two atoms which are adjacently placed, now those electrons would randomly arrange themselves in all possible directions. Therefore domains would have magnetic field, would have magnetic dipole moment randomly arranged in all possible directions. Let's first just write how a domain is formed, right? Then I'll show you what happens to the electrons in them, right? A magnetic substance consists of a large number of small regions. Consists of a large number of small regions. Consists of a large number of small regions called domains. Right? Now, how are the domains formed? Due to the interaction of unpaired electrons, due to the interaction of unpaired electrons in one atom with unpaired electrons in one atom with unpaired electron in the neighboring atom with unpaired electron in neighboring atom, the electrons spontaneously align themselves. The electrons spontaneously align themselves. The electrons spontaneously align themselves in a common direction over a small volume. In a common direction over a small volume, right? These small volumes so formed in uniform magnetization are called as domains. These small volumes so formed in uniform magnetization are called domains, right? So I can say thus the region of space over which magnetic dipole moments are aligned is called as domain. So therefore the space over which magnetic dipole moments are aligned is called domain. Fine, do you get this in clear? What are domains? Now, the magnetic dipole moments of the atoms in one domain are aligned in the same direction, right? Thus, each domain possesses some net magnetic dipole moment. Guys, they will be aligned in one direction. These are going to be randomly aligned in some other direction. These are going to be randomly aligned in some direction. You have random alignment. So you have random alignment in all possible directions. But inside a domain, the electrons are going to align themselves in same direction. Hence, each domain is going to possess some net magnetic dipole moment. Right? I can say that the magnetic dipole moment, the magnetic dipole moment of all the atoms in one domain align in same direction. Right? Thus, each domain possesses net magnetic dipole moment. Right? Now, what happens in the absence of the external magnetic field and in the presence of external magnetic field? Let's see. Ferromagnetic substance behavior in the presence and absence of external magnetic field. A. Let us consider a case in the absence of external magnetic field. Now, in the absence of external magnetic field, the different domains are oriented randomly in different direction. The different domains, in the absence of external magnetic field, the different domains are randomly oriented in different directions, are randomly oriented in different directions, right? They are randomly oriented in different directions, and therefore the magnetic field of these domains cancel each other. Therefore the magnetic field of these domains cancel each other, right? And as a result, the material does not show any magnetic effect. As a result, the material does not show any magnetic effect. Right, that's in the absence of external magnetic field. Now let's see in the with an application of weak magnetic field. With application of weak magnetic field. Now, with application of weak magnetic field, the applied magnetic field, due to the applied weak magnetic field, the individual atomic magnets tend to align themselves parallel to the direction of the external magnetic field. All the magnetic moments that are there in each domain, all of them will align themselves in the direction of the external magnetic field, and therefore the magnetic field, since all the domains will align themselves in the direction of the external magnetic field, therefore the substance will acquire some magnetic effect. Fine, do we get this thing clear? So here I can say with the application of weak magnetic field, the individual atomic magnets tend to align their axis parallel to the direction of the field. Their axis parallel to the direction of the field. The magnetic field is applied now these magnetic domains that have aligned themselves in the direction parallel to the field go on expanding continuously, and the domain size goes on becoming bigger and bigger, since all of them have aligned themselves in the direction parallel to the axis of the magnetic field. All these domains are in one direction, therefore the size of these domains, they will all go on fusing up, and the domain size will go on increasing. I can say that the domains in which the magnetic dipole moment are parallel to the field expand continuously expand continuously at the expense of the remaining domains right. Consequently, there is a shift in the boundaries between the domain. There is a shift in the boundaries between the domains. That's what I was telling you, that the size of the domain increases. All of them are aligned in the same direction. And ultimately the magnetic dipole moment aligns themselves along the direction of the magnetic field, right? And the magnetic dipole moment aligns itself in the direction of the magnetic field. Right? In the direction of the magnetic field. Now, if I remove the external magnetic field, what will happen? The domains will again get randomly aligned, the boundaries would again be formed, the size of the domains would be reduced, and as a result the substance would lose its magnetic properties. Right? If I can say on removal of external magnetic field, the boundaries between the domains, between
Sir, over there you said ferromagnetic substances are used to prepare permanent magnets, so which means they wouldn't lose their magnetic.
I will come to that. For that I need to place them in a strong magnetic field. I'll come to that. Right?
So over here,
let me just show you this, that they will randomly arrange themselves, but there will be some that will still be in the direction of the magnetic field. Right? I'll just come to that. Right? On removal of external magnetic field, the boundaries between the domains return. The boundaries between the domains return to their original position. And the substance loses magnetism. Now coming to your question, if the applied field is sufficiently strong, then the domain's axes are abruptly turned in the direction of the applied external field and the material would get strongly magnetized. In that case, if it is strongly magnetized, even after the removal of the magnetic field, the domain axis would not return to their original position and thus the substance would get permanently magnetized. This therefore is specified in the case of a weak field. This, instead of placing it in a weak field, if I were to place it in an extremely strong external magnetic field, then the domains would be permanently aligned in the same direction and therefore the substance would acquire permanent magnetization. Fine, do you get this? Simply, if you want, I'll write it down and give it to you. Take down. If the applied magnetic field is sufficiently strong, then all the domain axes abruptly turn in the direction of the direction of the applied magnetic field. The applied magnetic field. All the domain axes abruptly turn in the direction of the applied magnetic field. Therefore, the material gets strongly magnetized. Therefore, the material gets strongly magnetized. The material will get strongly magnetized. Now, even after the removal of the magnetic field, after the removal of magnetic field, even after the removal of the magnetic field, all the domain axes do not return to their original position. All the domain axes do not return to their original position. Right? Since all the domain axes do not return to their original position, the material gets magnetized permanently. The material gets magnetized permanently. That's how a substance would get magnetized permanently. Now, let's see something more about ferromagnetic substances. Let's try to understand Curie temperature. Now, I said that when a substance, a ferromagnetic material, is placed in a strong external magnetic field, all the domains would abruptly align themselves in an axis parallel to the external magnetic field. Even if the external magnetic field is removed, those axes would still remain aligned in that particular direction, and therefore the substance would acquire strong, would remain permanently magnetized. What if I start heating this substance? If the temperature of the ferromagnetic substance is increased, there would be random thermal motion of the electrons. If I heat the substance, the kinetic energy of the electrons will increase. That would result in random thermal motion of the electrons, right? And as a result of this, the coupling that has taken place between different atomic magnetic domains would become loose, and that would break, and thus the substance would lose its magnetization permanently. This is what happens when you heat the substance, right? Right. If a ferromagnetic material, I can say that in ferromagnetic material, the different atomic magnets are coupled together. Different atomic magnets are coupled together. Different atomic magnets are coupled together. Now, when the temperature of a ferromagnetic substance is increased, when temperature of ferromagnetic substance is increased, if I increase the temperature of this, there would be random thermal motion associated with atomic magnets. The random thermal motion associated with atomic magnets gets increased, right? As a result, the coupling between different atomic magnets in each domain would become loose and break. As a result, the coupling between different atomic magnets in each domain becomes loose. Becomes loose and breaks. Right? The coupling between the domains becomes loose and breaks completely at a certain temperature. Right? Due to this, the axis of the atomic magnet in each domain then get oriented in all possible direction and the domain structure gets destroyed. Right? I can say due to this, the axis of atomic magnets gets oriented in all possible directions. Due to this, the axis of the atomic magnet gets oriented in all possible directions and the domain structure is destroyed. Domain structure is destroyed. The temperature at which this happens is called as Curie temperature. Right? So I can say, therefore, the temperature at which domain structure is completely destroyed is called Curie temperature. Fine, did you get this thing clear? Thus, what happens at Curie temperature? I can say that thus, point number 1. Above Curie temperature, the ferromagnetic substance would get converted into paramagnetic substance. Above Curie temperature, ferromagnetic substance would get converted to paramagnetic substance. That's the first thing that happens at Curie temperature, right? And the Curie temperature is different for different ferromagnetic substances. Point number 2, Curie temperature is different for different ferromagnetic substances. Right? Okay. We'll stop this here for the day. Thank you very much.